So let's go ahead in this video and we'll look at solutions to the Jacobi Accessory equation. Now we've seen that we can write these partial derivatives in this form, and we've seen this in previous videos, so I won't go into that again. It allows us to then write the Euler-Lagrange equation in this format here, and also the Jacobi Accessory equation in this format here. Now a thing to note is that all of the solutions to the Euler-Lagrange equation are all of this similar form. We've got a function of x and also two parameters c1 and c2. So if you look back at the first course and you look at all the 10 or 15 examples we did, you'll be able to see that all of the solutions can be knocked into this general form. Now we're going to just state just now the solutions to the Jacobi Accessory equation, and then we're going to go and prove it. So if the Euler-Lagrange equation has got these general solutions, it turns out that the Jacobi Accessory equation has got solutions which are going to be given by the partial y by partial c1 here and partial y by partial c2. So this is the thing that we're going to prove through the rest of this video. So if this is the general form of the solution to the Euler-Lagrange equation, and this is the general form of the solution to the Jacobi Accessory equation, then you can see here that they're going to be related. So that means that if we were to differentiate this here with respect to the C1, we should get to the Jacobi Accessory equation. Equivalently, if we were to differentiate this here with respect to the C2, again we should get to the Jacobi Accessory equation. So we only need to do one of them, okay, so we'll just do this partial y by partial c1, and we're going to be differentiating this one here with respect to c1. So our f0 is partial f by partial y, but our functional here is a function of x, y and y derivative, but also the y and y derivative are going to be functions of the value of c1. So that means we're going to have to use the chain rule for differentiation. Equivalently, the value f1 is given by partial f by partial y derivative, and again our function f is the functional which is dependent on x, y and y derivative, and again the y and the y derivative are going to be dependent on the value of c1. So again we'll use the chain rule. So we're going to work through this using the chain rule. So we're going to have our partial f0 by partial y times our partial y by partial c1, and then we're going to have our partial f0 by partial y derivative times partial y derivative by partial c1. So that's just our chain rule for our differentiation. And then we're going to have the second part here, which is our minus d by dx, and again we're going to use the chain rule. So we're going to have partial f1 by partial y by partial c1, partial f1 by partial y derivative, partial y derivative by partial c1. So now let's call our partial y by partial c1 the value of u. So this partial y derivative by partial c1 will be our u dash. And similarly here we're going to have our u for this term here and our u dash for this term. So this has got this line here. So let's continue on the next page. So this is the last equation from the previous page. Now what we're going to do is we're going to differentiate out these terms here, and you can see we're going to have a product rule for differentiation. So we're going to differentiate this term and then multiply it by the u, and then differentiate the u and multiply it by this term. So that's going to give us two more terms, and we'll do the same here. We'll differentiate this term here and multiply it by the u derivative, and then we'll differentiate the u derivative and multiply it by this term. So that's going to give us another two terms. So we're going to get another 4 terms out of this, and we'll have the original 2 terms here. So we'll have 6 terms in the bottom line here. So this term here is the same as this one, this term here is the same as this one, and these two here are the product rule for the differentiation. So I'll just talk through one of them, and you can work through the other yourself. So we're going to have the value of u, so that's the value of u, and we're going to differentiate our partial f1 by partial y. So that's us differentiated, our partial f1 by partial y. And then we're going to differentiate our u, which gives us our u dash, and multiply it by this term here, which is a partial f1 by partial y. And we do a similar thing with this term here. Now just to note here, the final term here is going to be u dash, and it's going to be the d by dx of u dash, which is going to give you u double dash. So that's going to give us these 6 terms. Now what we can do is we can take the values here, partial f naught by partial y, and we can replace them by our simplified nomenclature. So this term here is going to be our f naught naught, this term here is going to be our f naught 1, and so on and so forth. This is f naught 1, and the 1 1 and the 1 1 here. And that was all equal to 0. And then we can add like terms or cancel like terms. So we're going to have their f naught 1 u dash, this term here, minus f naught 1 u dash. So this disappears here. So it's going to leave us with the 4 terms that we've got at the bottom. This is 1, 2, 3, 4 terms. And then what we can do is take out the common factor here of our u, and we've got this equation here. Now this equation here is nothing other than the Jacobi accessory equation. So we've just proved what we wanted to prove. So it means that the solution to the Jacobi accessory equation is going to be given by partial y by partial c1 and partial y by partial c2, where the values c1 and c2 are the solutions to the Euler-Lagrange equation. So that's all for this video. I'll get you on the next video. Goodbye.